I don't know if I wanted to think of any semester. Because like all my friends are like, yeah, it's super hard. It's worthwhile if you want to do something like that.
Mike, everyone.
At least you'll like stay awake and stuff.
First, a couple of small announcements. We are getting closer and closer to the end of material for this term. For instance, the assignment that we'll get this week is going to be the last written assignment for the term. There will be no new assignment in the week, so there will be assignment due next Friday, but not after this. We'll have 2 more web works, so the last week of the classes will have just the web work and no written assignments. The final is also somewhat close. We'll have much more information about the final as we get to the review week, the very last week. For now, let me say that the final will be going to be weighted much more heavily on the material after the midterm, so whatever you have not been tested on the midterm, but it will also include some problems on the material before the midterm. And in fact, we'll recycle one of the problems from the midterm. So, as a motivation for you to review the midterm and review the material before the midterm, well, we just tell you that we'll recycle all or part of the problem from the midterm for the final. So, if you at least go the midterm and know how to solve all the questions there, you'll have at least a place to start on the final without worrying about it. So please do review the material before the midterm, do review the midterm itself, and of course focus on the material after the midterm because that will be the bulk of the final assignment. And I'll talk much more about exactly what topics are going to be covered, but basically it's going to be all the topics after the midterm and all the topics before the midterm, but more emphasis on the topics after the midterm. Okay, so last time we talked about the chain rule. And the chain rule was a way to differentiate functions which were compositions of 2 or maybe more functions. So let me remind you what it was. Chain rule. So the chain rule applies to a function which looks like this. You take x, you compute some quantity, some function of x, and then you compute some function of the result, some function of g of x. And the question is, what is the derivative of this composite expression? And the answer was this. It's the derivative of m, but evaluated at the point g of x, multiplied by the derivative of g. So it's derivative of the external function multiplied by the derivative of the internal function. Or, equivalently, if you have a function of some parameter v, u is a function of v, and v itself is a function of x, so that you can express u as a function of x as a composition, u is u of v of x. Then the derivative of u relative to x, so if you take the function u and think of it as a function of x, so please take the composite function, is the product of 2 derivatives, du by dv times dv by dx. And we had some simple examples last time. Let's start with one more simple example this time, and we'll go on to solve much more complicated examples today. So, example. What is f prime? What is derivative of this function, sine cube of x. such question, the first question to ask, well, first question is of course, what kind of rule do I want to apply? And sometimes the answer might be ambiguous. For example, here, there are several choices. You might want to try to apply the product rule, because you see this function sine cube of x is in fact sine of x times sine of x times sine of x. So you might apply the product rule. Arguably, the chain rule will work even better here. So let's try to see how the chain rule will work. If I decide that to try a chain rule, I should recognize that my function is a composition of two functions. Is that true? Alright. So I want to recognize this function as a composition of two functions. And what functions do I have in mind? I want to write this as, well, first I take x, then I compute some quantity in terms of x, and then I compute some other quantity in terms of the previous result. So how do I decompose this computation into two steps? Okay. And which operation is the first one? Which one is the second one?
The first one is execution. Oh wait, do you mean the first one in terms of
So
which direction are you going?
So I start with x.
Okay. Oh, then it's sine of x is the first one.
Okay, good. So when I compute this expression, think about it this way. I start with x, then if I were to compute this expression on calculator, let's say, for a given value of x, I'll plug in x, then I will compute what is sine of this number x, and then I'll take whatever the result is on the display of the calculator and find the cube of the result. So first operation is sine of x, the last operation is taking the cube of the answer. So here I'll apply the chain rule like this. The last operation, this is going to be the external function, the last operation, is taking the result of whatever you already computed and finding the cube of it. And the first operation was taking x and finding sine of x. So this will be usually referred to as external function. And this is going to be referred as the internal function. So the internal function is whatever you do to x, and then the external function is whatever you do to the result of computing the internal function. So here I first compute sine of x, and then I take the result and find the cube of it. Well, once I've written my function as a composition, I just apply the chain rule. So I see that I have to compute du by dv, dv by dx, and that's what I did. Du by dv is if u is q, what is du by dv? Recall that this is just the derivative of q if you regard v as the unknown quantity. 3b squared. Thank you. Similarly, what is dv by dx? If v is sine of x, what's dv by dx? Cosine of x. And now I can write the result. It's 3 times v squared times cosine of x. The only thing is, I don't want to express the answer in terms of v. V is, just for my convenience, it's an intermediate step. My final answer should be all in terms of x. Because my question was in terms of x, I want the answer to be in terms of x. But that's easy. V, I know what v is. It's sine of x. So here it is. The derivative of the external function multiplied by derivative of internal function. So notice this kind of small subtlety. Let's say that I remember the chain rule in the following form. The derivative of the composition of two functions is the derivative of the external function multiplied by derivative of internal function. That would be correct, but here's a small subtlety. Derivative of internal function sine of x is very easy. In this case, it's just cosine of x. Derivative of external function was taking an argument and finding this argument cube. I know what the derivative of cubing operation is. It's 3 times the argument squared. So I have 3 times something squared. What's important is that this something is the argument of the external function. Here, whatever I'm finding the third power of is sine of x. So that's what goes here. So it's 3 times the argument of the external function squared. Okay, so any questions about this example? Maybe let's contrast it with the following example. Sine of x cubed. What would be the derivative here? So this is also a composition, but it's a different thing. If I want to find the value of this expression given x, let's say I have a calculator, what I'll do is first I'll take x, then I'll find x cubed, and then I'll take the result and find sine of the result. So in this case, the last operation that I'm doing, the u, the external function, is finding the sine of the result of the previous computation. And the previous computation is just taking x and finding x cubed. So here I have quite different u and v, because here I do the two operations in different order. I first find x cubed, and then I find the sine of the result. Well, once I recognize what's the external function, what's the internal function, it's really easy to find, so to apply the chain rule. Derivative of sine of v is cosine of v, derivative of x cubed is 3x squared, and I plug it back here, so it's cosine of v, v is x cubed, times the derivative of internal function. So once again, it's the derivative of the external function, which was sine, so here's cosine, evaluated at its argument. The argument was x cubed, so it's evaluated at x cubed, multiplied by the derivative of the internal function, which was derivative of x cubed, 3x squared. Is there any questions about either this exercise, that exercise, or why the two are different? How the two are different? Well, let's move to some more complicated methods. So, with the chain rule and with all the other rules that we already know, we can basically write any function, just any expression, however complicated, and then we'll be able to find its derivative. Maybe let's do an exercise. Let's say I'll ask somebody to give me a function which can be pronounced in, let's say, 5 seconds. And we'll find the derivative of this function. So our next example, I'll need a volunteer. Somebody to come up with any function. There is no right answer or wrong answer, just any function. I'll remind you that we have the building blocks for building the function. These are powers, sums, products, quotients, compositions, logarithms, sines, cosines, e to the power. So basically, start by saying, random words. Sine of x to the power 1 of whatever. The only limit is, 5 seconds. So please, any volunteer. Okay.
Cosine x squared plus x to 3
Okay. Okay, let's say this was our function. Okay, so first question is, how do we approach finding the derivative of this expression? Oh, by the way, I didn't ask you, was it cosine of x squared and brackets closed, or cosine of whatever was here?
No, it's fine.
Okay. Okay, so here we have a function. What's the last operation that we do here? The very last thing. Sorry? I heard somebody say something, but I didn't hear what it was. The addition, yes. So here we compute this expression, that expression, and the last operation is find the sum. Well, what's the derivative of sum? It's the sum of the two derivatives. So first step is to recognize the derivative of sum is sum of two derivatives. Now we have split this problem, this complicated problem, to two simpler subproblems. How can we approach the first subproblem? Finding the derivative of cosine of x squared. What rule should we use? The chain rule. So this function is not a product, not a quotient, not a sum, not a difference, but it is a composition of two simple functions. It's cosine of x squared. Okay. So here we recognize that the external function is cosine, internal function is x squared. Well, since this example is pretty similar to what we did over there, let's do it a little bit faster than we did it there. So we want to find the derivative of the external function. Derivative of cosine is minus sine, evaluated at its argument. The argument was x squared, and multiplied by the derivative of the internal function. What's the internal function?
2x.
Okay, so internal function is x squared, its derivative is 2x. So that's the derivative of this expression. I applied the chain rule. What about the second expression? X cubed times 2. What kind of rule should I apply here? Second? Okay, I could, yes. So, for example, I can recognize that this is a product of two functions, and I can apply the product rule. You'll see that it's not the only option here, but let's go with this one. So I have a product of two functions. I apply the product rule. X cubed prime times 2 plus x cubed times 2 prime. I copy this expression. There is no more that I should be doing here. Nothing more. So I already don't have any derivatives. I can rearrange the terms to simplify it a little bit, but let's just leave it. Here, derivative of x cubed. What kind of rule should I apply here? Power. Derivative of x to the power n is n times x to n minus 1. Times 2 plus, and what's the derivative of 2? 0, because 2 is not changing with x. The rate of change of the number 2 is 0. It's not changing. It's always changing. So it's x cubed times 0. And finally, I have this answer, minus 2x sine of x squared plus 6x squared. That's the answer. And that's basically the thought process for solving any problem. You look at the expression, you think, what is the last operation that has been performed? If it is one of the operations, product, quotient, sum, difference, you apply the corresponding rule. Product rule, quotient rule, sum rule, difference. If it is evaluating some function, if it is a function of x, just find the derivative. You know what are the functions, what are the derivative of ln x, sin x, cosine x, e to the power x. If it's more complicated, if it's a function evaluated at some complicated expression, apply the chain rule. So regardless of what the situation is, you have a rule to apply. You know how to proceed. Another remark, here, when finding the derivative of x cubed times 2, you could have done a little bit better. You could have skipped the product rule altogether and recognized that this was just a constant multiple rule. If the derivative of a constant times a function is the constant times the derivative of the function. And 2 is a constant after all. So the derivative of x cubed times 2 would be 2 times the derivative of x2, which is right here. But it doesn't matter. Even if you apply the product rule, well, you'll have one extra step here, but in the end it will work out. The derivative of a constant turns out to be 0, so the answer is the same. So any questions about this exercise? Okay. Let's do something. Really complicated. Just to see that we can. Let's find the derivative of e to the power square root of ln of x squared plus 1 over x squared plus 1. So here's a really horrible expression. I mean, it is horrible. You have composition of lots of functions, you have quotients, you have logarithms, square roots, all of them. We still can find the derivative.
Is that all in the exponents?
Yes, it's e raised to this whole power. So what's the approach? What is the last operation? If you were to compute this thing on the calculator, what would be the very last thing that we would be doing? E to the power, yes. Okay. So the last operation was take the result of all previous stuff and find e to that power. Okay. Now we have to decide, is it e to the power x, for which we know the answer, or is it e to some complicated expression? Which one? So of course, e to the power of complicated expression. So we should apply the chain rule. Chain rule. For chain rule, we have the following pattern. We should recognize what is the external function, and that's just what we said. It's e raised to the power of whatever we already computed. An internal function is, well, this whole terrible expression. Du by dv is pretty simple. It's e to the power b, because derivative of e to the power b is e to the power b. The derivative of b Well, it's complicated, so let's leave it as the derivative of v. So let's write that this is e to the power of v right here. 1 of x squared plus 1 of x squared plus 1 times derivative of this. Okay, so we are not done yet. We still have to find the derivative of this. So let's, on the side, solve this problem. What is the derivative of 1 of x squared plus 1 of x squared plus 1? Once again, the question is, what is the very last operation that you are performing when computing this expression? The square root, yes. So if you are computing this on a calculator, you compute all this thing, and finally you take the square root of the result. Once again, is it square root of x itself or square root of a complicated expression? Well, of course, square root of the complicated expression, so we should apply the chain rule. Okay, so chain rule once again. The last operation is square root of the result of previous computations, and previous computations are 1 over x squared plus 1 over x squared plus 1. Du by dv, what is the derivative of square root of v with respect to v? Right. So square root of v is just v raised to the power 1/2. So to find the derivative of this, I apply the power rule. Derivative of v to the power n is n times v to the power n minus 1. So here it is 1/2 times v negative 1/2. Well, so it's 1/2 times 1 x squared plus 1 over x squared plus 1 negative 1/2 times the derivative of v. So derivative of v is the derivative of this expression. For now, I'll just leave it like this. I'll just leave it as the derivative of 1 of x squared plus 1 over x squared plus 1, just because it's still too complicated to find the answer right away. But now I can advance one step further. I'll try to find the derivative of this expression, 1 of x squared plus x squared plus 1. First question, am I kind of going in loops here, or am I actually advancing in the direction of the final answer? So, did we get to simpler questions from the initial question, or are we just going in loops and we started with a derivative, next question was a derivative, next question is a derivative? So, what's your opinion? Are we getting towards the answer?
Yeah.
Yes.
Totally.
Simpler, of course. This expression is already simpler than the initial one. The initial one contains this expression, but it also contains two extra operations, square root and e to some power. This is way simpler. Okay, so let's continue. What's the last operation in computing this thing? The very last thing that you do if you want to compute this thing. Logarithm, yes. So after you found this result, you'll find the logarithm of this. So once again, it's logarithm not of x, but rather something complicated. So I write that I compute logarithm of something complicated. This complicated part is this thing. And apply the chain du by dv is 1 over b. Derivative of logarithm of b is 1 over b. And I'll have this result 1 over b, 1 over x squared plus 1 over x squared plus 1 times derivative of b. Okay, still have to find the derivative of this, x squared plus 1 over x squared plus 1. What's the last operation here in this computation? Addition. After I compute this thing and that thing, I'll find its sum. Well, so what rules should I apply? The rule for the sum. The derivative of the sum is sum of the two derivatives. X squared plus prime plus 1 over x squared plus 1. Right. The derivative of x squared is finally something really simple. What's the derivative of x squared? 2x. That's the power. So once again, the last operation, in this case the only operation, is raising to the power, so apply the power. Here, what's the last operation that I'm doing here? So I'm trying to find 1 divided by x squared plus 1. Imagine yourself using a calculator, what would be the sequence of operations? More interestingly, what would be the very last operation that you perform? Division. Well, I heard actually two great answers. One answer was the last operation is division, the other answer was taking 1 over the answer. So both would work. You can approach this question, this part in 2 different ways. I would say that the last operation is division and apply the rule for division, which is the quotient rule. Or you can say that the last operation is taking the result of previous operation and finding 1 over e. And then you'll find, well, you'll apply the chain rule. So maybe let's do both. Let's see how both work. I'll split the board and perform the same computation in 2 different ways. To find 1 over x squared plus 1 prime, I can apply the quotient rule, because the last operation was division. And what's the quotient rule? Well, derivative of numerator times denominator, 1 prime times x squared plus 1, minus numerator times derivative of denominator, divided by denominator squared. And final simplification, 1 prime is 0. So nothing here, and numerator I have derivative of x squared plus 1, 2x. Yes, so it's sum of the 2 derivatives, derivative of x squared plus derivative of 1, derivative of 1 is 0, derivative of x squared is 2x. That would be the answer. Or I could argue that I have such a situation. I'm trying to find the derivative of this expression, and instead of thinking that the last operation was the division, I would say that last operation was finding 1 over the result of previous computation. So apply the chain. U is going to be 1 over v, and v is going to be x squared plus 1. Should also work. Du by dv. Well, 1 over v is v to negative 1. So du by dv is minus 1 times v to negative 2. That's the power rule. And dv by dx is 2x. So using this, I'll find that the result here is minus v to negative 2 x squared plus 1 to negative 2 multiplied by 2x. Did I get the same result here and there? Well, yes, because if you raise something to negative 2, it's the same as finding 1 over this thing squared. So this is the same as minus 2x plus 1 over x squared plus 1 squared, which is exactly the same thing as it was here. So regardless of how you approach this, you'll get the same answer. And of course, well, if you are on an exam and that's the question, after performing all these intermediate computations, you should come back and write the answer. The derivative of e to the power square root of 1 over x squared plus 1 over x squared plus 1 is e to the power square root of 1 x squared plus 1 over x squared plus 1 times 1a over 2 square roots of 1 x squared plus 1 over x squared plus 1 times 1 over x squared plus 1 over x squared plus 1 times 2x plus 2x over, sorry, minus 2x over x squared plus 1 squared. So we just combine all the intermediate results together. We have e to the power of the whole thing times this part, 1/2 times this to minus 1/2, which is the same as 1 divided by 2 square roots of this thing, times 1 over this thing times the very last thing that we computed here. Okay, so please questions about this very, very long computation. So the thing about this computation is, yes, it is very long, but in a way it's also rather simple because each step is rather simple. Each step was just one basic application of one of the rules. The chain rule, the quotient rule maybe, the sum rule, one of the rules. So it's like having, I don't know, a cabbage. It has many, many layers, but if you want to get to the core, well, you basically peel one layer at a time. And that's exactly what happens here. You first peel off the e to the power something, then you peel off the square root, then the logarithm, then the sum, then the quotient, and finally we get to really simple stuff. So once again, any questions, please? So now I'm going to discuss some standard tricks how to apply the chain rule in situations where it doesn't seem like it is applicable. So some standard tricks. Let's say you want to find the derivative of 5 to the power x. Unfortunately, it's not quite one of the things that we talked about. it's not really a composition of things. It is just one operation, taking 5 and raising it to power x. So chain rule doesn't seem to be applicable. It's not a polynomial. It's not sum of x to some powers. It's not product quotient. What else? It's not e to some power. It's not sine, cosine, logarithm. So it seems that we are facing an actually new function. One of the functions which we cannot differentiate. Well, it is true, but we can write it in a way that will allow us differentiation. Here's the trick. The trick is to write 5 as e to some power. After all, any positive number can be written as e to some power. So let me write 5 as e to what power? So I need your help now. I want to write 5 as e raised to some power. What power should I use? 1 of 5. Yes. So in general, I have the identity that if I take e and raise it to power 1 of whatever number z, I get z back. Because 1 is exactly the power, 1 of 5 is exactly the power to which you should raise e to get 5. That was the definition of 1. Okay, so let's go back to here. I'll write 5 as e to the power 1 5. It looks a little bit stupid. I mean, I complicated the expression. It used to be 5 to the power x, now it's e to the power 1 5 times x. Well, yes, I did complicate it, but the positive thing is now I have e raised to some power. And I do know how to differentiate e raised to some power. So first thing, I'll rewrite this as e raised to the power 1 5 times x. That's a rule for differentiation. X raised to power, well, yes, a raised to the power b and then raised to the power c is the same as a raised to the power b times c. So here, instead of raising first to the power 1 5 then raised to the power x, I raise it to the power 1 5 times x. And now I can find the derivative using the chain rule. After all, I have e raised to some power, and this power is some complicated expression. So the chain rule would be compute e to some power, and b power is 1 5 times x. Maybe it's a good idea to actually put the brackets here, just so that we don't get confused with 1 of 5 times x. It's not. It's 1 of 5, and then multiplied by x. So du by dv. What's du by dv? e to the power b. What's du by dx? What kind of rules should I apply here? Okay, good. Is there a simpler way? Okay, let's apply the product. So it's 1 5 prime times x plus 1 5 times x prime. What's 1 5 prime? What is it? Okay. What's, let's say, derivative of 1 of e? First question, what is 1 of e? Okay, maybe let's approach it in a different way. Derivative of 1 of 5. So I heard that it was 1 over 5. Does anyone have an objection to this? So what you have in mind is derivative of 1 of x. Derivative of 1 of x is 1 over x. Is this relevant to finding the derivative of 1 of 5?
It's 0.
It's 0. 1 of 5 does not depend on x at all. 1 of 5 is not changing with x. 1 of 5 is just a number. It's something like 1.6. I'm not sure what it is exactly, but it is a number. So it does not depend on x. The derivative is 0. So back to here, we have e to the power of v, 1 5 times x, times derivative of v, which is 0 times x plus 1 5 times x prime. X prime is 1. That would be the answer. If you want to simplify it a little bit, well, e to the power 1 5 times x is in fact just 5 to the power x. We already have seen it. So let's say that it's 5 to the power x times 1 5. Before I go to a more complicated example on the same idea, let me go back to this point of derivative of 1 5 being 0. Suppose that you somehow did not recognize that 1 of 5 is actually a number. You thought that it was a composition of two functions, one of something. And you wanted to differentiate it using the chain rule, or well, whatever. So, remark. One 5 prime is 0. Either because 1 5 does not depend on x, so that would be the simplest explanation why the derivative here is 0. But let's suppose that you did not recognize that 1 of 5 does not depend on x. How would you proceed? Well, the thing is, you still might try to apply the rule that the derivative of logarithm is 1 over its argument. It will not be a mistake. The only problem is, you should remember that the rule is derivative of 1 of x is 1 over x. Here it's not 1 of x, it's 1 of 5. So in this sense, it's a composition. It's logarithm of some expression, not quite x. Some expression which is not x. So what you should do here is apply the chain rule. We'll say that the last operation is finding the logarithm of the previous thing, and the previous thing happens to be just 5. So, du by dv is 1 over v. That's what we know. What's the derivative of 5? Zero. Now it's quite obvious. Now we cannot confuse it with anything. It's not a complicated thing. Derivative of a number is 0. So here it will be 1 over 1 of 5 times 0, which is of course still 0. So even if you don't immediately recognize that 1 of 5 is a constant, still you should recognize that it's not 1 of x. So it's not the rule for 1 of x which is applicable. It is 1 of something else. Well, apply the chain rule. It will lead you to the correct answer. Okay, so see you Monday, and we'll continue with this in the next couple of days.